Just quick refresher on covariance matrices. You kind of don't need this, but actually you sort of do. They come up in PCA, they come up in Kalman filter, they come up a lot. You should know what covariance is because multivariate normal distributions come up a lot, and they use covariance. So what is variance? Here are some numbers, and the mean of them is 3. The deviation is the average of how much they differ from the mean. So the first one differs from the mean by 1, the second one differs from 0, the third one differs by 1, quantity divided by, now we either divide by 2 or 3. Do we want the biased or the unbiased estimate of variance here, or of deviation, excuse me? And the answer is usually the unbiased, so we'll divide by 2. What does that mean? I've already been over it.
It means we had sample distribution well.
Yeah. The nice thing about this is the answer doesn't matter because given enough data, the problem becomes vanishingly trivial. Therefore, don't worry about it so much. But when you deal with small numbers, you're really supposed to divide by n minus 1 because, think about it this way. Suppose you have a number, 7. What's the mean? 7. What's the deviation?
0.
Aha. The deviation of this number is 0, but the deviation of the model from which this number was drawn could be anything. You see how that's a nan? It's a 0 divided by 0. So it should be 0 divided by 0. Because that's what nan is yes, there's an answer, but we're not going to tell you what it is because we don't know. Right? So you're supposed to divide by n minus 1 because you really take 2 things in order to measure spread, if that makes any sense. Okay. Suffice it to say, that's deviation, which in this case is 1. Square it, and it's 1. So the variance of that is 1. I should take that back. The variance of that is not 1. The variance of that is 2/3 squared, which is 4/9. But the variance of the model that would produce numbers like that, the best estimator of the variance for that model is 1. There, now I'm being technically correct. Okay. We get what variance is. What is covariance? Well, now you have a bunch of data. 2, 4, 3, 6, 7, 8, 9, 2. These pairs represent observations. So each row is an observation. I have made 4 observations. And I have 2 numbers each time I make an observation. Why? Because I have 2 sensors. Maybe both of them are laser distance measurers. And one's shooting to that wall and one's shooting to that wall. And I could measure the centroid and variance of where my robot is in the room relative to the distance of the walls or something like that. Or they could be a 2-pixel camera. Why you would have a 2-pixel camera, I have no idea. But the point is you could have 2 sensors and you can measure them 4 times if you want. Therefore, here's some numbers. And you can measure the variance in each column, right? It's just this number squared, that number squared, that number squared. Well, subtract the mean, square the numbers, take the average, there's the variance. Covariance is a very similar concept, except you're doing the product between them. So we're saying, on average, after subtracting the centroid, what's the product between these 2 columns? Does that kind of make sense? At least at a sort of intuitive level. The equation for it ends up being x minus x mean times y minus y mean quantity summed 1 over n minus 1 if you want the unbiased estimator. Is that correct? I feel like I'm forgetting a denominator here.
No, I think that's right.
No, that's the denominator. Yeah, I think that's right. There's covariance, not a complicated concept. It's just the same as variance, except you're just taking pairwise product, right? Now, if you have only 2 columns in your data, do you see that you're going to compute the pairwise variance of every pair of columns. So this column with itself, that's the variance of column 0. This column with itself, that's the variance of column 1. And then this pairing, and then that pairing. I just flipped my hand over. didn't point it to the same two. So that's why covariance is always a square matrix, and the diagonals are always the variance. So this corner always is the variance of the first column in your data. And this one is the variance of the next one, and so forth down the diagonal. And this element here in blue is the pairing of column 1 and column 2, and it's the covariance among them. And the covariance between column 2 and column 1 is going to be the same as column 1 and column 2 because multiplication is commutative or transitive or associative or whichever one of those properties says you can do it both ways. I totally should know that, but at the moment it's not coming to me, and you got to look it up. And is that commutative?
It's commutative.
It's commutative. Okay, thank you. Okay, and kind of surprisingly, this equation and this way of representing variance produces a matrix, and then you just do linear algebra, and it just works as if you were doing deviation, or variance rather. In other words, this really is a multivariate generalization of the concept of variance, and so you can use a covariance matrix just like it's a normal number. And all of your simple algebra suddenly turns into linear algebra, which it turns out is kind of the same thing. You just do it in MATLAB instead, and it all works out. And the multivariate normal distribution is just a normal distribution in multi-dimensions. Okay? So I think you can handle that. The only thing you really have to be able to do is this linear algebra. And here's what you'll need. You've got to be able to do matrix multiplies. Can you do that? I think you can because matrix.h, let's see what I supply to you. Come on, no faster. Multiply. There you go. I provide a function to you that multiplies two matrices. You pass in matrix A and matrix B, and you can even transpose them if you want to, and it handles that for you and returns to you a matrix. If you want to write good C++ code, make sure to delete that matrix when you're done. If you're familiar with auto pointer, that's even better than delete because it attaches a local variable to it that deletes the thing when it goes out of scope. That way, if an exception gets thrown, you still don't leak memory, and that would be good C++ style. Okay. So there, I've provided matrix multiply for you. Let's see what else you're going to need. Oh, so we got a function. We'll deal with that in just a minute. There's a multiply. There's another multiply by the transpose, but I already provided that for you. There's another multiply by the transpose. Matrix multiply, matrix multiply, matrix multiply. Inverse. Ah, there's a nasty one. How do you do matrix inverse? You ask Dr. Gashler to write some code for you, and then you say, thank you so much for sparing me from having to do matrix inverse. You're welcome. Okay. In fact, this returns a pseudo-inverse. What's the difference between a pseudo-inverse and an inverse? Yeah, so I don't like the term pseudo-inverse because pseudo to me means not quite. And pseudo-inverse is actually not quite an inverse. It's more than an inverse. So I think it's a badly named concept. But pseudo-inverse, you should be aware, is what they call the Moore-Penrose pseudo-inverse. In fact, let's look that up. Moore-Penrose inverse. I think they're now calling it the Moore-Penrose inverse instead of pseudo-inverse because people have started to figure out that pseudo is the wrong term for it. Nope, they're not. But the pseudo-inverse is a generalization of inverse. In other words, if you take a matrix and you compute the inverse, and you take that same matrix and you compute the pseudo-inverse, it's always the same. Pseudo-inverse can do anything an inverse can do and will always give the exact same answer as an inverse. The problem is there are matrices which are not invertible. And the pseudo-inverse, in those cases, doesn't throw an exception. So inverse throws an exception. It says, math just died. Divide by 0. Can't handle it. Pseudo-inverse says, well, even though this matrix is not invertible, I will return to you the least squares approximation of something that inverts it. In other words, if you compute the pseudo-inverse and then you multiply it by itself, wait, no. If you take the pseudo-inverse and then you invert it again, it's as close to that original thing as you could get in the universe. Does that make any sense? While minimizing over some squared error. And in cases where the matrix is invertible, that's exactly equal to the inverse of the matrix. Therefore, you may comfortably use pseudo-inverse wherever inverse is called for, and you may be even more comfortable because if the matrix is not invertible, it'll just do the right thing anyway. As it happens, in the Kalman filter, this product is always invertible. Therefore, you should be able to use Gaussian elimination or your own favorite matrix inversion technique to do this. But just in case, due to numerical instability or due to whatever reason, it's not quite invertible, because that happens with computers. You end up with a number that's supposed to be 0, and it's actually represented as negative 0.00000001, and then all of a sudden it freaks out when you try to do a square root or something like that. Okay, well, in that case, the pseudo-inverse will do the right thing and return something that's approximately correct. So I like the pseudo-inverse because it doesn't freak out and tell me I can't do math when I'm doing it right, whereas computers otherwise do. Sorry for talking so fast. I get that way when I'm summarizing. Do you get what pseudo-inverse is? Okay. Just to show you how much work I've done on your behalf, let me show you the code for pseudo-inverse here. Where is it? Basically, it's 90% of this file. This is actually the function. It starts here, scrolls down here, scrolls down here, goes to there. Okay. It's not that bad, but it's kind of a nasty function to implement. There you go. The Moore-Penrose inverse is actually built on top of singular value decomposition. So if you can do singular value decomposition, inverse is actually really easy. Turns out singular value decomposition is a really hard problem and can only be solved iteratively, so they have all these iterative processes for it. Truth is, I didn't really design that code. I swiped it from numerical recipes in C and then modified it to fit with my code and all that. If you have any trouble with pseudo-inverse, it's okay to say, I don't know what's going on, that's not my problem, Dr. Gashler, help, because I should be able to debug that better than you. So if you end up getting nans from your pseudo-inverse operation or something like that, don't sit there banging your head against it that you didn't write that, that's my problem. But it should work because I've tested it a lot of times in a lot of ways, and I think it's pretty darn stable. Done this for a couple of years, so I think you're good. Just be aware that sometimes bad stuff happens. Okay. You'll need inverse and more matrix multiplies. Matrix addition. That's easy, right? Okay. Matrix subtraction. Yeah, okay. Oh, that's even vector subtraction. Subtraction, multiply. That's it. So just a whole bunch of matrix multiplies, additions, and subtractions, and that one inverse right there, and you can do the entire Kalman filter. Can you handle that? Okay.